Thursday.
Okay, you
10
tell me
questions,
how to
10
position.
minutes. And we're starting for the rest of today on muscle tissue. We'll talk about as much skeletal muscle tissue physiology as possible. And then Thursday after the exam, we're going to continue and finish out the muscle chapter. Good? So that will include a little bit about smooth, a little bit about cardio. All right. So let's see. Ooh, oh, reminder slide, right, of anatomy, skeletal, smooth, cardiac. And woo! Reminder slide, anatomy, building, skeletal muscle. So there they're showing us a bicep up there, and then we slice it open. We've got a single muscle cell. Remember, that is our muscle fiber. Packed inside each muscle fiber, we've got a myofibril. We build myofibrils out of these thin and thick filaments. We're going to go nuts with this today. So be sure that you know this cold. Good? All right, this is all about this. All right, so to be sure that it's hammered back into our heads, thick, thin filaments, thin actin, right? Thick myosin. And remember how we're going to build. Here are extreme close-ups. We've got our 2 strands of beads made out of actin subunits, and we're going to add on top of that, because we've used actin in other places, right? That's all anatomy stuff. But here in muscle tissue, we're going to add, especially specifically skeletal muscle, we're going to add to our actin, right? Our 2 strands of beads. We're going to add 2 additional things. 2 additional things. So we're going to add this and this. You see those 2 pieces? So we're going to save those details for just a moment. Let's keep that in your head. And then here, this we should know already, myosin, right, with the little kind of balloon heads sticking up. We're also going to add more details to that. All right. And be sure that you remember how we put them together to build a sarcomere, right? We've got alternating, right? Alternating filaments. And if we were to 3D this, right? See how that's like 3D, right? We have more out here and more out here. We alternate, always alternating. And also with some overlap. You see we've got overlap there. And we can kind of modulate that overlap with, I don't know if you can tell in this projection, but if you look, you know, on your screens and printouts, I hope it's clearer. See these little sort of spring-like little pieces of a separate protein, titin. So we're going to add that to our anatomy knowledge, right? Because that was kind of a detail in anatomy that we kind of glossed over. But we've got these spring-like pieces of protein holding this overlapping shape, sort of maybe at a particular level of tension, even in a relaxed state. So tighten, there we go. And we're going to be able to, because it's a spring-like shape, we're going to be able to, just like a spring, stretch it and it will recoil, right? All right. As far as all the lines and zones, I just want you guys to focus in on the Z line, because that's the most recognizable line. All right. Let's see. Let's add our details now. We'll do actin first. So, this blue, maybe rope-like piece of protein. This one, the blue. Tropomyosin. So we're just gonna add that in, right, to our knowledge. Tropomyosin. And maybe sitting on top of that tropomyosin, you see in pink, these little blobs, right? Troponin. So you see both of them start with the prefix trop, right? So don't get them confused. Oh, brother. Trop. And this rope one has myosin. Oops. Oh, no. This is bad, right? Because everything's starting to sound the same. Uh-oh. So for sure, put everything right in the correct box. Right off the bat. No good. So let's see. Let's look at another little detail. On each actin molecule, if we really look up darker spot, right? Like a darker purple spot. And you see it, here's one here. On that actin, which is a lighter purple, right? And we also see that the tropomyosin, it seems to be here in this picture anyway, a little bit covering the dark spot, right? Can you kind of make that out? All right. So that's on purpose. The dark spots on the actin molecules are representing myosin binding sites. So on actin, we have binding sites. We know what binding sites are, right? Okay, so that shouldn't be anything new or shocking. So we have binding sites, and specifically, they're just representing them with the dark purple dots, right? And specifically, these binding sites are for, myosin. All right. And it turns out in this configuration, this tropomyosin seems to be covering the dots, covering the binding sites, right? Okay, so far so good. Let's see. And let's look over at myosin. Up close, the myosin heads. Remember myosin heads from anatomy, the kind of balloon-shaped things on the top. In purple, luckily they match, right? In purple, we've got actin binding sites. Does that seems like, actin would bind here, right? So does that make sense? We're going to allow myosin to bind on the myosin binding sites of actin. The other side of that coin, right, is that the actin binds, right, at the actin binding sites. Good. So these purple dots, right, it's like matching. The purple dots fit together. Good? All right, the purple dots fit together. Awesome. On myosin, on the heads, it looks like we have a separate second binding site. Kind of this dark red over here. Oh, ATP. ATP binding site. Oh. So probably we're going to have some ATP bind, and maybe we'll use it. Right? Let's see. A few chapters ago, we went through a whole process, right, to make ATP. And depending on where we were in our series of processes, right, we could make a little ATP or we could make a whole lot of ATP. And depending on what fuel we used, we could make a whole lot of ATP or we could make a really whole lot, right, of ATP. Remember? All those things. Good. So, we're not going to make ATP for no reason. We're going to use ATP. So far, we have seen in the previous chapter, nervous system, we used ATP, didn't we? We used ATP to create a resting membrane potential, right? We picked sodium potassium ATP ACE pump, and we had to use ATP to create that whole resting membrane potential, blah, blah, blah. We know that, right? All right. Now, completely separate deal, right? Separate deal. So keep that, right, over there in the nervous system chapter, right? For now. It's going to come back and haunt us. But for now, we'll keep it over there. Now we've got a whole different item, myosin, and specifically the myosin heads, and we have a binding site on the myosin head for ATP. We're going to use that. So we've got now our second location where we are going to use some of that ATP that we made with all of our processes, right? Glycolysis, Krebs, oxidative phosphorylation. Good? All right. Let's see. And just to say it one more time, troponin, right? A little complex of globular proteins sitting right on top of that tropomyosin. Take note, there seems to be a little, see that little notch, little shape there? That's probably a clue, isn't it? If you've got a protein that has a little shape, right? We're probably going to use it. Good? All right, keep that in your head because we are. Let's see. anatomy review, the thing I want to draw your attention to would be this area here. Let's remember and bring it to the very front of our heads. The blue. What is the blue stuff? Oh no, that's a gray. That's a gray. The blue, yeah, sarcoplasmic reticulum. And we remember from anatomy, sarcoplasmic reticulum's job was, I don't know if we remember from anatomy.
Yeah, it's like a net to hold the myofibrils in place.
No, not really hold them in place. I mean, they do surround,
Yeah.
right, myofibrils, but they had a job. Of course, we didn't talk about the job because that's physiology, but we mentioned the job. No, not waste. Not waste. We had to store something.
Calcium.
Calcium. Oh my gosh, we're gonna store calcium. We're gonna store calcium. Oh, this is it. Today's the day, right? Today is the day. Let's see. So we're gonna store calcium, and then in gray, the T tubules. T tubules. You see this little cutoff part, but let's look over here. You can see that the T tubules, we should know this from anatomy, are continuous with the whole plasma membrane or in muscle sarcolemma, right? And you see that here, continuous, it dips in deep, right? And it is arranged in such a way that you see how it's next to sarcoplasmic reticulum. They butt up right against each other. And this is going to become important. Good? All right. Woo! Oh my goodness, we got a couple of definitions. Contraction. So far, like coming into class, most people think of a contraction like when you contract the muscle and then you can, I don't know, like pick something up, right? And I've contracted bicep muscle. Right, that's what most people think of for contraction. But we're going to have a very specific definition for contraction for physiology class and muscle tissue physiology. We're going to say that contraction really is activating cross bridges. And remember, from our picture, when we are going to get those myosin heads to bind to that actin, right, at those binding sites, that sort of shape, right, is a cross bridge when that's attached. So cross bridge, we get the cross bridges to attach. That's activating them. When that happens, we will, using some processes that we're going to talk about in a second, increase tension in the tissue. Increase tension. That's contraction, increasing the tension. Not necessarily shortening the muscle. If I pick something up, right, and contract the bicep, and I want this to come closer to my face, right, that's shortening the bicep. And that's usually what most people think of as a contraction. But if I pick this up and contract the bicep, but I don't actually bring this close to my face, then this is still contracted, right? If I brought with me some weights, they're light weights, but, right, let's pretend this weight was too heavy for me to manage, right? You can see it's the muscle still contracted, right? But let's pretend, no way, right? It's still contracted, but I'm not shortening, right? That would still be contraction. All right. So, let's see. So we have all that. Relaxation, opposite of that, right? Just turn that whole thing off. Decrease tension. It does not necessarily mean lengthening the muscle. Good? All right. So, it could, but not necessarily. So, let's see. We're going to talk about neuromuscular junctions. Neuromuscular junctions and see how can we get motor neurons, somatic motor neurons specifically, to communicate with these muscle fibers. Right? So that's our first order of business. So we're going to have these neuromuscular junctions, the places where those axon terminals of the somatic motor neurons are going to meet up with our muscle fibers. All right, so let's take a look. We've got here one motor neuron with many branches reaching out to, there we've got 5, right, different myofibrils, and we'll call that one motor unit. Here, we've got two motor units because we've got two separate motor neurons, and each one has some branches, right, going to the different myofibrils. All right, good. So we're going to keep this in our heads. We're going to apply this later. Okay, we'll apply that later. So just keep that in your head. Oops, just a little review. These motor neurons, I already said somatic, right, as opposed to visceral. No, visceral doesn't go to skeletal, right? And we're talking about skeletal for now. Visceral is going to go to what? If we're talking about going to muscle fibers, what muscle types? Huh? Smooth and cardiac. Good, smooth and cardiac. So keep in mind, just for this part of the discussion, skeletal. Focusing on skeletal. As far as the neurons are going, afferent or efferent? Efferent, right? Exit, going out. Afferent is all the stuff we just did. So, sensory, right? Afferent. Okay. Let's see. Here is a close-up drawing of a neuromuscular junction. You definitely want to memorize this drawing, right? And then we're going to have an extreme close-up on the next slide. But let's take a look at what we've got. We've got our somatic motor neuron axon and axon terminal. There's a patch of myelin there. And we've got some synaptic vesicles. Woo! Oh! Containing our old friend, acetylcholine. Always, right? So that's hopefully simple. We're only dealing with acetylcholine at neuromuscular junctions. We don't have to worry about all those other ones, right? Acetylcholine, nice and simple. Great, thank goodness. Okay, so acetylcholine over here. And then here, this is the muscle cell over here. And I kind of bracketed that off. This little section of cell membrane, motor end plate. Motor end plate. So we've got that. And, looks like, what is the deal with, I don't know, making this sort of, these folds, right, in the membrane. What are we doing? We talked about this a lot in anatomy. When you increase like folding or fingers sticking out. Increase surface area, beautiful. It will increase surface area, right? We could probably put more receptors on more membrane, right? Super smart. All right, very good. And then we see down here, looks like sarcomeres, right? Down here. Okay. Let's see, I think we've got our extreme close-up. Yes. All right, extreme close-up. Oh, this looks terrible, doesn't it? Oh, there's a lot of numbers, like 1, 2, 3. There's many steps. But it's okay. Some of these steps, like we actually already know, it just doesn't seem like it yet. All right, so let's see. Action potential arriving, right? All right, and of course, voltage-gated calcium channel. We know. Oh, and of course, signal vesicles release acetylcholine. We know, right? Good. All right, acetylcholine hanging out in synapse, right? Synaptic web. We know. And of course, receptors. We know for acetylcholine. What about receptors? Wait a second. Just time out for just a moment. What were our receptor types for acetylcholine? Nicotinic? Muscarinic. Woo! Right. Always, right? Always for neuromuscular junctions, nicotinic. So that made it simple, right? Whew! For the time being, not for too long, but for the time being, we don't have to think about muscarinic, right? All right. Take advantage, right? Just let's do that for an hour, not even an hour, right? Let's just think about nicotinic. Woo! Let's add a little bit of information to nicotinic. Ligand-gated sodium, potassium channels. Do not confuse, I should put that in italics. Do not confuse these with sodium, potassium, ATPase pump. Because that could be easy to do, right? And if it showed up on some sort of exam, like an exam whenever this one comes up, or right? Because I haven't said it today. Exam, you don't want to, don't let me do it, right? Don't let me confuse you. All right. So nicotinic, neuromuscular junctions, ligand gated. What's our ligand? The ACH, right? The acetylcholine, of course. Oh, awesome. All right. That's our ligand, and we've got these. Now let's look up close. Here they are, right? They've drawn in these. These are sodium, potassium, ion channels, not ATPase pumps. Not ATPase pumps. So when the acetylcholine binds, because it's the ligand, right? When it binds to the nicotinic receptor, it opens, right? So closed, bind. You can barely see it, right? But you see these little bits of acetylcholine. Opens, right? And here in the book, they are emphasizing sodium coming in. There is potassium exiting, but because there is so much more sodium entering than potassium exiting, the book has just shown us that, but I kind of added in. We still have to acknowledge, at least I feel like, we still have to acknowledge that there is potassium that's going to exit. There's just so much more sodium coming in than potassium leaving. All right, I mean, that's just the way the ion channel is set up. But it is an ion channel built for both to move. Good? All right, so that's going to happen. Because we've got so much sodium coming in compared to how much potassium is going to leave, what are we going to do to, oh, you see all these charges? You see these charges on either side of this sarcolemma? See? All along here. Aha. Remember, let's take a little detour. Remember when we first talked about resting membrane potential, right? Way back, way back. And way back then, we had said, oh, like every cell in the body, right, has that, right? Has sodium, potassium, ATPase pumps working to create and maintain this resting membrane potential. And in different cells, we might end up with different, right, resting membrane potentials. And then we spent a whole chapter, actually 2 chapters, focusing on neurons, right? And we had motor neurons, and we had sensory neurons, and then we saw a couple of examples of sensory neurons that actually had different, remember, resting membrane potentials we just saw today. And hearing, right, different resting membrane potential. All right, so that was all neuron stuff, but now let's come back out. Now we're in muscle tissue, specifically skeletal muscle, and skeletal muscle cells are cells, and they have sodium, potassium, ATPase pumps embedded all over those membranes, creating a resting membrane potential. Good? All right, so this muscle cell has its own resting membrane potential created by its sodium, potassium, ATPase pumps in the sarcolemma. And we see the charges all lined up because of that. All right, so if we open up our nicotinic receptor, which is an ion channel that's going to allow a whole lot of sodium in and a little bit of potassium out, we just let a whole bunch of positive charge in and a little bit of positive charge out. So if we let a whole bunch of positive charge in, what happens?
More positive.
Aha. Just look, well, it became more positive, right, on the inside. In neurons, what did that create? Created potential, and specifically an EPSP, right? It was like going in this direction. positive, right? In a positive direction. So EPSP. So we're gonna create something that is very similar, right? Very similar. But instead of calling it an EPSP, like we did in neurons, we're just gonna call it an end plate potential, because here we are in muscle tissue at the end plate, right? This motor end plate of the skeletal muscle. Good? But it's incredibly similar to an EPSP in neurons. Good? Be sure that you've got that concept, right? Try to get that to sink in for sure. And, again, especially for final exam, read that carefully, right? Because it's awfully close.
So similar as in its graded potential?
Exactly. All right. So we have just created this end plate potential. And here's our abbreviation, EPP. Oh, brother. Close, right? Oh, but I'm warning you. Right? So it's fair. So anyway, EPP. Not to be confused with EPSP. They're incredibly similar. All right, so we've just created our end plate potential at EPP. Very good. Let's follow the arrow. That, because it is a voltage change, can travel. Just like a graded potential, right? Our EPSP is the same. So that's also same, right, or similar. So it's going to travel to this patch of membrane over here, right? It's just outside of, this area under the synapse. All right, and we're going to have a new set of receptors. Ion channels. Sorry, scratch that. New set of ion channels. Look at this. Voltage-gated sodium channels. Separate, different from our nicotinic receptors, right? Right? Nicotinic receptors, ligand-gated, accepting acetylcholine. Over here, we're out from underneath that synapse, that neuromuscular junction, and we pick from the pie a different channel. What we're going to pick is voltage-gated sodium channels. Go ahead.
And that's because of EPP? Like, how did that?
We pick this because we're gonna do something different, right? We have to take this EPP that we created here. We allow it to influence this membrane because it's all continuous, right? We allow it to influence this part of the membrane. We pick a different channel from our pie. We pick a voltage-gated one because this is a voltage, right? So we should pick a voltage-gated channel. I mean, we know this stuff, right? So we pick a voltage-gated channel, allow sodium, right, to pass through, so that when the voltage arrives in the form of an EPP, it opens, and then sodium will come in. So far, so good? All right, sodium comes in, and that means positive charge comes in over here. We are going to create a muscle fiber action potential. We have not seen that yet. We're going to see it, like, I don't know, in a couple slides. Good? But here, with these different ion channels that are not the receptors, not nicotinic receptors, right? They're voltage-gated sodium channels. We're going to be able to create a muscle fiber action potential, which is different from a neuron action potential. We have not seen it yet, so don't ask me that question, because we're going to see it. Go ahead.
So ACH ligand binds to nicotinic receptors to open up sodium and voltage, gated channel.
Ligand.
Ligand gated.
This one first is ligand gated.
Right, but that's opened up by an ACH,
Right.
and then, but by that binding, does it also open up that area that you're pointing to right now?
Yes.
Okay.
Like when you go from here, like in this drawing, when you go from here to here to here, that's like a sequence.
Okay.
That's as if we were looking at the same exact receptor. Here it is closed, here it is bound and open, and here it is, because it's open, letting sodium in.
Is it important to know that the voltage gated is outside of the synapse?
Yes.
Okay.
Absolutely. That's like key. Good, huh?
So is voltage gated letting all those positive ions out?
No, 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 no. What this is doing over here is first receiving this EPP, which is like a graded potential in a neuron, but we're in muscle.
Okay.
But it's still a voltage change, right? So this channel is sensitive to voltage because it's voltage gated, and we've seen this before, right? Like that concept. We're just in a different location, right? We're in muscle. So just like all the voltage gated channels that we've seen so far in neurons, this one will respond to a change in voltage, which is an EPP, by opening, right? So when it opens, because we also picked, it happens to also be a sodium channel, it'll fit sodium, right? When it opens, that's what it allows through. Like it's not the right charge inside to let calcium through, right? Which was our other example, right? We've seen calcium before, voltage-gated calcium, right? This one's built for calcium, this one's built for sodium. Good? So what's going to go through? Sodium. And when sodium goes through, that's a lot of positive charge. In this completely separate location, right? That's the other thing that you absolutely have to get, is that this is separate from this. Good? Two separate locations.
So both of them are allowing sodium in, but in different locations.
Exactly. Exactly. And different mechanisms. Here, this is a ligand-gated channel responding to acetylcholine. This is a voltage-gated channel responding to voltage. Good? All right. Super important. It's totally fine for you guys to like keep like asking to be sure, because this, if you can get this, right, the whole rest of this chapter will be much better. Go ahead.
So letting in all that positive sodium charge is going to eventually lead into an action potential.
Right. However, this action potential is specifically a muscle fiber action potential. We're going to see, we haven't gotten there quite yet, but we're going to see in the next slides what really a muscle action potential really looks like, and how is it similar and how is it different from a neuron action potential. Good? All right, so we're going to take this and we'll talk about it in a minute, right? So just, we know this is going to happen. Huh?
I think Shirley asked that, but Shirley asked this, but is the synapse, or sorry, the voltage-gated sodium channel is happening outside of the synapse?
Exactly.
Okay.
Exactly. And maybe it would be more accurate and more correct to maybe, and I should do this myself because I keep saying synapse. Let's change from saying synapse to, for sure, neuromuscular junction, right? Because I know I kind of said synapse also a few times. I mean, we sort of have, it's really like half a synapse, right? Because this is a neuron, but this is really muscle. So to be very proper, we should say neuromuscular junction, right? I mean, yeah, it works an awful lot like a synapse, right? And a lot of times, a lot of people, most people actually still say synapse. But to be super, super, super proper, right? We would really say neuromuscular junction. Having said all that, right, about being proper and everything, yes, these voltage-gated channels are completely physically separate from the area of this neuromuscular junction. Yeah. Good. Good. Okay. Woo. So far, I think hopefully so good. Like I said, we're going to look at this in just 1 minute. Like, what is a muscle fiber action potential? Hang on to that. Let's just finish out before we leave this picture. We'll tie up some loose ends, and then we'll return to what is a muscle fiber action potential. We'll spend quite a bit of time looking at that. All right, so set that aside just for a moment. Let's see. We've done all this stuff. Meanwhile, while all this stuff is happening, right? Meanwhile, we do have acetylcholine, like still there, right? Still hanging out, and we should do something about that. And we did mention a little bit when we talked about neurotransmitters and we talked about acetylcholine. We did mention this enzyme, acetylcholinesterase, right? When we talked about acetylcholine in the chart, right? So now let's talk one more time about acetylcholinesterase. So here in our neuromuscular junction on the muscle membrane, let's go ahead and embed that enzyme into the membrane so that once we have bound the acetylcholine to our ion channel and opened it up and it did its job, right? It let sodium in and a little bit of potassium out, right? Once it did all that stuff, it can unbind, right? And bind to our acetylcholinesterase, which we see here actually, right? We see here. And if we have any extra floating around, I mean, that's what they're showing you here, right? It's binding to acetylcholinesterase. Good. The point is, we're kind of done, right? With the ACH that we released. We're done. We don't want it to hang around, right? Let it bind to the enzyme. It's right there, embedded in the membrane. Handy. Smart, right? Put it there where we need it. So that while this stuff is floating around, let's just bind there. And we already know, break down, right? Choline, let's let that come back in to be recycled. And then our old friend acetyl coenzyme A, of course, also we can recycle. Great. All right. Very good. Very good. If we have returned, right, broken down and returned for recycling our components of ACH, we no longer have ACH hanging around, right, in this space. So no more is going to be binding to these ion channels. We go back to our closed position and we stop the flow of ions here, so we stop creating EPPs. Done. Make sense? All right. Hang on. Oh, I made this kind of bigger before we leave, just to really, really like hammer this into the head. All neuromuscular junctions are considered to be excitatory. So remember in neurons, sometimes we had EPSPs and sometimes we had IPSPs. Neuromuscular junctions, all EPPs. Good? All. All right. No other choice. Let's see. So let's start to look at what is a muscle fiber action potential. So here we see a picture. Bloop, bloop, bloop. It's a little bit like a neuron action potential, right? Let's look at some of the differences. Big difference right off the bat. Right, we'll start at -90 as our resting membrane potential for skeletal muscle tissue. So there's right that resting membrane potential that we're just going to stick that in the head. All right, good. Looks like, the maximum's the same, right? +30. That's similar. And then we come back down, and again, it's going to be a steep, right? A steep curve up and down. And we do overshoot a little bit at the bottom, and then we come back to normal. Maybe that happens a little more quickly than it did in neurons. But overall, that's kind of the same, right? Similar. All right, cool. Now let's look down here. Here we're looking at something new on our y-axis. And this is going to now be muscle fiber tension. Tension. So we're going to talk about this a lot for the rest of today. Tension here. And again, and we've got time over here. Let's look at this particular line, which is representing the muscle contraction. And remember, our definition of contraction was creating tension, right? So depending on how much tension we create, will be up higher on the line, right? So it looks like when muscle fiber action potential happens, we create an increase in tension. And at some point, we will kind of max out on that and then taper off and relax. Good? So that's what this line is about. They're also pointing out a little period of time that's kind of like, okay, we create this and there's just a little latent period, right? Because we have to wait for some things to happen, which we're going to see, to wait for some things to happen, and then the muscle starts creating the tension. All right, good. So, let's see what has to happen. What has to happen. So, this nut. Here is our title. Excitation, contraction, coupling. So this is how we go from an EPP and then an action potential, right? Muscle fiber action potential, all that electricity, right? To all that voltage, to tension. Tension created by, remember cross bridges? All right, so we have to couple these two actions together. And we call that excitation, contraction, coupling. So let's see the process. All right. This process is complicated. So we're going to go step by step. All right. So first, let's arrange our items that we've got in our sarcomere, because it was within the sarcomere that we were going to have those cross bridges, and this is where we're going to create the tension. All right. So actin, myosin. Myosin heads with the actin binding site, our little dots, right? Oh, I'm sorry, did I say myosin? Myosin with actin binding sites, actin with myosin binding sites. Good? Little dots, little dots. They're going to match up. But remember, we were going to start off with our little dots on actin being covered with that blue string, tropomyosin. Tropomyosin. All right, and let's take a look at troponin, our little globs of protein with the notch. See how the notch doesn't have anything in it? All right, this situation here is when the level of calcium in the cytosol is low. Low, so hardly any calcium in the cytosol. All the calcium is in the sarcoplasmic reticulum. It's still in storage, right? Let's be sure that we realize that these thin and thick filaments, these sarcomeres, are in the cytosol, right? They're like kind of hanging out in the cytosol. And our calcium is inside sarcoplasmic reticulum. Remember the anatomy, right? Remember where that sarcoplasmic reticulum is kind of forming like a net around all those myofibrils, right? All those sarcomeres. Good? Okay, so remember that. Good. So when we've got all the calcium in storage, right, or most of it in storage, here's our situation. All right. Let's release a whole bunch of calcium, right, from the sarcoplasmic reticulum into the cytosol. We'll talk about how we do that. Let's go ahead and release calcium. Ooh, look at that. That calcium fits into that little notch in the troponin. That's handy, right? Because we know, of course, it's like kindergarten by now, but we know if something fits into a binding site of a protein, we can change the shape, right? Awesome. So we're going to change the shape not only of the troponin, but of the tropomyosin that the troponin is sitting on. And look what happens when you change the shape. Do you see how now these binding sites for myosin are exposed? So it's like we bind the calcium, we change all the shapes, and we pull the tropomyosin off of the binding sites. Good? When we expose the binding sites, look at that. You see they just fit. Good? So we fit, cross bridge. Good? We created the cross bridge. Make sense? All right. Let's take note before we go to the next slide that I have in here energized. And I have here energized. Why would I put a word in? There must be something to that, right? Like, why would I put in that word? ATP. Yes. ATP. We're going to see, I think it's in the next slide, we're going to see that we need to bind the ATP first to the myosin heads to what's known as energize, right? Energize the myosin head. We're going to change the shape of the myosin head, and that's considered to be energized. All right, so take this. Let's see what we're going to do. All right, here we go. This should look familiar, right? Down here, let's kind of move up here. We should recognize this as a schematic drawing. Of course, it's not realistic, right? This does not look like how our anatomy is, right? These are like gigantic, and then this is like tiny. We know, right? The schematic drawing, so we can see different steps. But here we have our representation of sarcoplasmic reticulum, and we know calcium, right? Calcium is stored here. And we see here, this is our representation of a T-tubule. And we realize, aha, continuous with sarcolemma. Now here's another one, continuous with sarcolemma, right? All right, let's see. Here they're showing us a muscle fiber action potential. And we already saw what that is, right? And we know how we created that, right? So we've got our action potential traveling along sarcolemma, and when it hits a T-tubule, I mean, it's continuous, right? With the sarcolemma, so it's just going to dip down, right? It's going to travel, right? Down into that T-tubule, because it's continuous. So that's what this arrow means. So it's continuous. Oh, whoa, whoa, oh, we're running into something, right? Let's look at the extreme close-up of what did we just run into. It's embedded in the membrane of the T-tubule. Let's see. Looks like we have a calcium channel. Perfect, right? We're storing calcium here in this sarcoplasmic reticulum. Maybe that's a good choice. That we should pick a calcium ion channel from our pie, right? If we want to maybe release it. Good? All right, so we're going to pick that. Looks like that calcium ion channel is in fact embedded in the membrane of sarcoplasmic reticulum. Smart, perfect. We could have thought of that, right? If we would have just put that effort in, right? We could have thought of that. All right, so we've got calcium ion channel embedded in sarcoplasmic reticulum. Awesome. So far, so good. Looks like we have two other items. They seem to be attached, right, to that calcium ion channel. They do have names. They are receptors, and I put parentheses around them because I felt like it's getting a little crazy as far as details are concerned. But we'll acknowledge, okay, it's not just a plain calcium ion channel. It's a calcium ion channel with some special attachments, right? Special attachments. But we're just going to know that the special attachments help that calcium ion channel to sense the voltage, that action potential arriving. So we can generalize and say this is a voltage-gated calcium ion channel. It's just, it has a couple of attachments to help us with the voltage, right? Fine, fine. Basically, voltage-gated calcium ion channel. A little bit special. All right. So, see where that is? Like where it's situated? And here's the close-up. So this dark blue is inside sarcoplasmic reticulum. This light blue is, I guess you could say inside T-tubule, which is really continuous with outside, right? Like extracellular. Okay. And then this yellow, oh, what is yellow? What is the yellow part? Oh my goodness, it's a cytosol. Oh, huh. So let's see. When we open up that channel, when that action potential arrives, right, and that's voltage, so we open the channel, calcium, ooh, goes in the yellow part, into the cytosol, right? So I put that in capital letters. Cytosol. Oh, wait a minute. So now we've got calcium in the cytosol. That's going to bind on our troponin binding site. We're going to change the shape. We're going to pull that that tropomyosin off of those binding sites, right, on the actin, and now our energized myosin heads can bind, which we saw in the previous slide. Good? And remember, they bind when we had a high calcium level in the cytosol. Good? So this is how we made that happen, how we made our cytosol concentration of calcium high, right? We released it from sarcoplasmic reticulum into cytosol. Good? Using basically a voltage-gated calcium ion channel. Huh? It's not bad. Not bad. All right, let's see. Before we look at more of these details about the contraction itself, let's see, we can't let the calcium stay there forever, right? Otherwise, we might end up constantly creating cross bridges. I mean, we're going to want to relax at some point, right? Relax the muscles. So, we should have a mechanism built in to return the calcium back to the sarcoplasmic reticulum, right? Let's pick from the pie. Pick from the pie. Looks like an ATPase pump, right? ATPase pump. If we were to look back at the pie, we're not going to pick sodium potassium ATPase pump for this location because that's not what we're trying to do. What we're trying to do is pump calcium. So let's pick the calcium ATPase pump. Make sense? So, I hope that at this point, now that we've gone through, since we established our pie, right? We've gone through neural tissue, and we've gone through sensory physiology, and now we're in muscle tissue and muscle physiology. I hope we're starting to see the pattern that we keep picking from the pie, right? And depending on what we want to accomplish, you just pick something different from your pie, right? If you can remember what you're trying to do and remember your choices in the pie, you can probably figure it out if you happen to forget, right? I know that's making it sound more simple, I know, than it really is, right? But I'm giving you a little bit of a clue. Yeah, there's going to be a lot of memorization. We've got to memorize the pie. We've got to memorize all these processes. But sometimes you'll forget, you know? Like, which one? Which one? Brother, which thing did I need from the pie? Well, if you remember, we're dealing with calcium, right? That's, we got to get rid of the calcium. We got to get rid of the calcium. You know, that'll at least narrow down our choices in the pie, right? You might be able to narrow it down to, like, in your memory, right? You might be able to narrow it down to, oh my gosh, I think I could choose like a calcium ion channel that's voltage gated, or I could choose like an ATPase pump for calcium, right? So you've narrowed it down to two. That's better than nothing, right? It's better than I don't know, right? So do you see the process? All right, so we're constantly choosing from the pie. All right, so let's take our calcium, our calcium ATPase pump, embed it in that sarcoplasmic reticulum, and then when we're kind of done, right? And we'll talk about how we're going to be done. But when we're done, let's pump the calcium back in, right? Pump it back in, pump it back in, pump it back in. As you get rid of more calcium from the cytosol and put it back into sarcoplasmic reticulum, do you see this two-way reaction over here? If you keep taking away calcium from the cytosol, we remove calcium from troponin, right? If we remove calcium from troponin, we revert back to the original shape and we cover the binding sites. And so if we cover the binding sites, no more myosin can bind. Good? This is good. This is pretty efficient, right? This whole system. Let's see. All right. So here, let's look specifically at the cross bridges. All right. So here we've got cross bridge, and in dotted lines, that's supposed to show us this action of swiveling, right? These myosin heads will swivel. They'll bind, swivel, and then detach, and then bind. When it swivels, when it does the swiveling, the actin is moved, like that whole unit is moved, right, in this direction. And then this will detach, bind to, I don't know, a binding site over here, swivel, and then that'll push the actin even further, right? And then it'll detach and then bind to the next one and keep going, right? Kind of like, right, like boom, 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 boom. Something like that. All right, so we've got this happening on both sides of the sarcomere, and the actins come closer together, right? That's the result. And that drags the Z lines closer together just because it's all attached, right? So this, right, would be shortening, right? We have tension here when we bind, and then when we swivel and detach and then attach, swivel, detach, attach, we shorten. Good? All right, let's see. Oops, wait a second. There. So let's finish out this this contraction part of this excitation contraction coupling. So I like to start this discussion here at this step, going from here to here. So here we've got actin with what do they? I guess they have calcium already attached to it. So the purple is our calcium. So they have already kind of released all that calcium. But here we've got actin. I want to focus in on that myosin head. Here we have A standing for actin, M standing for myosin, and then the dot with the ATP means, ATP comes in and binds, right? So here we see ATP coming in and binding to the ATP binding site of our myosin head. Okay. We should also know that myosin is an ATP ACE. We've already heard about ATP ACEs, right? We can take ATP, we can take off that phosphate, we have ADP and a phosphate, that's what an ATP ACE does. We know that already. So, here's another example of an ATP ACE, or myosin, right? Specifically the myosin head. So, ATP binds to the myosin head at the binding site. This ATP ACE, known as myosin, does its job. Oh, hydrolysis. We haven't said that word in a while. Hydrolysis. And look what we've got. There's our phosphate group and there's our ADP, right? They stay attached to that myosin head. That's energized, right? Which we mentioned before. So here we've got now an energized myosin head. Energized myosin head. Looks like, let's see. Okay, looks like here we do not have our calcium, right? Calcium is released, which we saw already. Calcium is released into the cytosol. It binds to troponin, changes shape, drag the tropomyosin off of those dark purple dots, right? The binding sites. This energized myosin head attaches. We swivel. See the change in shape here, right? Swivel. And then to get this to detach, we need to bring in another ATP. Good? We need to bring in another ATP because during the swiveling we lost our ADP and our phosphate because of the shape change. Those fell off. Good? So to detach, we've got some space, right? Because we lost our ADP and our phosphate, and the shape changed. So we can bring in an ATP and allow that to attach to the myosin head. And we're ready. Do you see how we're ready for round 2? And now we can let the energized myosin head attach to the next binding site. Swivel, ADP phosphate fall off, ATP comes in, we detach and energize, and then we attach to the next binding site, right? And that's that whole bind, swivel, detach. Bind, swivel, detach. Good? But now we're adding in, how do we energize? How do we energize? And we have this built-in ATP ACE to do the energizing. All right. We could go around and around and around as long as this muscle is contracted, right? So as long as I want to hold this thing, right, I can just keep going, keep going, keep going, keep going, keep going, right? Woo! And if I wanted to shorten, especially, right? Oh, keep going, keep going, keep going, keep going. Good? All right. So, the point is, how can we possibly get out of this, right? I mean, of course, we're going to tell, right, using motor neurons. Okay, stop, right? We're going to stop the release of acetylcholine in the first place. We'll talk about that later. That's kind of our next topic. But as far as getting out of this contraction cycle, right, to get these myosin heads to detach, we know that we need the ATP, right, to get them to detach. All right. What if we ran out of ATP? Huh? We'd do what? It would stay attached. It would stay attached. So this is what this arrow is showing us in a situation where we run out of ATP. Oh, we stay attached, right? We stay attached. This is actually the situation of rigor mortis, right? So after someone dies, not breathing. If we're not breathing, what are we not doing? Oh yeah, oxidative phosphorylation, right? Oxygen. Yeah. So no ATP. Oops. So this is why after death, no oxygen, no oxidative phosphorylation, no ATP, the muscles, right, seem to get frozen in position, right? So this kind of starts to take place. I mean, it starts, right after it builds up, and then about 12 hours after, we've got kind of maximum, right? Maximum seeming to be frozen in place. After that, right, so that'll stay for a while. But then, once you get, like about 4 days out, right, or so, everything starts to loosen up again. Or no, it's like 2 days out. But everything starts to loosen up again because by that point, the muscle tissue is actually breaking down, like totally breaking down bacteria, et cetera, decomposing. So if stuff is breaking down, well, everything's going to loosen up. Okay? So this is how people can start to figure out, like, if you don't know the exact time of death because you weren't there, right? You can start to figure out, well, can we narrow it down, right, to 12 hours ago or 36 hours ago or greater than 60 hours ago, right? You can narrow it down based on, is the person still in rigor mortis or not? Is everything loosened up? Good? All right, let's see. So here we've got a summary slide. Woo! And I know sometimes I tell you, oh, the table, if this makes it worse, don't worry about it. If it makes it better, worry about it. This is one of those ones I kind of like you to worry about anyway. So try to get this one. Because here we see in one place different areas where we really need ATP, right? Muscle tissue. So first, we've got sodium-potassium ATPase pump, right, in the sarcolemma or plasma membrane. So, like, right up front, we have to create that resting membrane potential. I mean, we know that from before, but we shouldn't keep it. We should keep it in this table because we don't want to forget, right? That's like how we create this whole entire thing in the first place, resting membrane. All right, so we've got that. And then we had our calcium ATPase pump embedded into the membrane of sarcoplasmic reticulum. We used that to get that calcium out of the cytosol and back into storage, right? When we're done. Okay, so that's location number 2. And then we had ATP on our myosin heads. And remember, our myosin heads are also an ATPase. Not a pump, right? But an ATPase. So we have it here, myosin. Okay, so we just saw that. And here they've kind of broken that down into two. One is hydrolysis and one is the binding in the first place. But those two you can think of together. Good? All right. Let's see. I think, and this is just in words, that whole entire sequence. This is one of those slides, if this helps you, go with it. If this makes it worse, go with the pictures. Right? All right. I see you like, oh yeah, I'm going with the pictures. That's okay. Let's see. So, this is definitely a good cutoff point. Let me just see where we are. Okay. Good. That's good. All right, so this is where we're going to cut off for today. So we're 6 minutes early. Awesome. We will, on Thursday, have our exam, right, on sensory. 10 minutes, done. And then we'll pick up here. So we write down where we're picking up. Tension. Okay. We'll pick up where tension is. Woo! Good. Very good. So, that is going to be